I'm so glad to be here and present our work, ARTEMIS, that is about the adaptive bitrate ladder optimization for the live streaming. ARTEMIS is by collaboration with different university and research institute, Concordia, IMDEA, and Chicago University. Okay, what's a live video streaming in a pipeline? In the live streaming, we have a live camera that captures the content and continuously send to the origin server on the cloud to encode in different representations. In the origin server, we need a bitrate ladder consists of the pairs of the bitrate and resolutions. This bitrate ladder constructed by the content-aware or context-aware or agnostic to the content and the context. Based on this strategy, we have a fixed bitrate ladder in traditional video streaming, live video streaming. And then after having this bitrate ladder, encoder produces content in different quality and resolutions, and also we have a manifest file. This manifest file includes different parameters regarding the streaming and video, and the manifest also consists of the different bitrate and resolutions that's given by the bitrate ladder. After that, the data is on the CDN server, and the video player can start streaming by sending the HTTP request and receiving the HTTP response. So inside this pipeline, we focus on the player side, that we have one ABR algorithm here. This ABR algorithm considers different parameters, for example, buffer, bandwidth, and based on the strategy that we have in the ABR objective function, for each segment, we have a desired bitrate determined by the ABR algorithm. And then by having the manifest file, ABR tries to find the best bitrates inside the manifest. If it doesn't fit to the exact bitrate, then looking for the lower one that is the highest for that bitrate. For example, here, 4.6 megabit per second is desired by the ABR, and then the ABR select 2.4 bitrates. So we have a gap here, 2.2 megabit per second, at impact on the quality of the segment that we need to receive and underutilized bandwidths. So the highest bitrates might be too low. Why? Because here, for example, we select for the 8.0 megabit per second, but we need to select the highest one in the manifest is 4.8. We have here 3.2 gap. Also, in the worst case, we need to download 0.5 based on the different parameters, for example, the available bandwidth or different situation, and then we need to select 0.8, that is excessive bandwidth and high start probability here. So let's consider two ABRs here, for example, L2A ABR and LO plus ABR with different network conditions, LTE network and the cascade network. And also we have one manifest file here, is a fixed manifest file with the 5 bitrates inside. So you can see here that there are horizontal lines here in the gray color, and there are advertised bitrate in the manifest, actually 5 bitrates in the manifest, and predicted bandwidth by the ABR. Then the ABR select here the red cross points here. That is different, is a gap between the predicted one and the available one here. As you can see, the gap between the selected one and the available bandwidths. So we cannot say that, okay, based on the available bandwidths, we can select the best bitrates to download the next segment. So how can the bitrate ladder accommodate better desired bitrates and help players? Here, ARTEMIS proposes a mega manifest for the better bitrate alignment. In the mega manifest, we can add many bitrates inside the manifest. Here, for example, 50 bitrates inside the manifest. And then we can let player to have better selection of the bitrates. This mega manifest is studied during the streaming. And also, this mega manifest can decrease the gap between the desired one and the served one. For example, if player select, for example, 4.6, then served by 4.5, that is close to the desired one. So here, in this experiment, let's continue that experiment with the consider mega manifest here. In this case, you can see that the green dot points here, that is close, is higher one than the red one, that is the red one based on the 5 bit race. But here, by advertising 90 bit race, we can see that the player can select better bit race in terms of the quality. But how? Here, we need to also take a look on the bit rates, on the quality that affected by the bit rates here. You can see, for example, here, the comparison between the different contents, for example, sport and documentary, for different bit rates and resolutions. We measure the VMAF. Actually, you can see here that based on the increasing bit rates, we can have more gain in terms of the VMAF. It means that a good bitrate ladder should be aware of the video quality also. So, another problem that we have here, this impact of the mega manifest on the live encoder. We cannot apply the mega manifest to produce all 50 bit rates inside the manifest, because it's very time consuming and we need to have more high computation and also bandwidths, and the CDN side we need more storage to save all contents. ARTEMIS aims to adaptively select an optimal subset of the mega manifest that lets player to have better quality of experience. This subset should be based on some predicted quality indicator from the encoder side, and also we need to receive some logs from the CDN, and should be end-to-end. Consider the player, consider the encoder, and also should be agnostic of the player and ABR types. ARTEMIS is also in time slot fashion, is operating in the time slot fashion here. Here you can see the ARTEMIS in a glance. So we have the mega manifest that advertise different bit rates to the players, and then we have the selected bit rates by the players. From the CDN server, we can collect all logs about the players, and also from the origin side, we can have the all quality factors, and then produce OTL, that is stands for optimal temporary ladder for that time slot here, and then apply on the encoder side to encode the segments based on the neo OTL. But we have here, for the OTL, we have some challenges, how to select the OTL, which constraints should the OTL impose, and also when should the OTL be updated. Actually here, we demonstrate some constraints that we need. For example, in the OTL, in determining OTL, we need to first consider those bit rates that are requested by the clients. We can, for example, based on the statistics that we have from the CDN, we can find out, okay, these bit rates are desired by the clients. And then we have one, for example, constraint here that at most we need to select 3 bit rates inside the OTL. And then we can select some of them, but the other that we omitted should be served by the lower one. For example, if we omit 3.4 here, then we need to serve the request for the 3.4 by 2.8. Another constraint that we need to consider here is the traffic reduction, how much we can reduce the traffic here. For example, here you can see the frequency of the bit rates that requested by the clients, and then based on serving the clients with the lower bit rates, we have some bit rates saving here. The last one, but not least, is the quality improvement. How much we can improve the quality, or how much we have degraded quality by the serving with the lower bit rates. By having these informations, we can define an objective function, as you can see here, maximizing the bandwidth, also the quality degradation. And with these parameters that you can see here, the alpha is very important here because it's making trade-off between these two terms, and is very important for the calculating OTL. In terms of the time complexity, it's very interesting that showing here that determining the OTL, it doesn't depend on the number of the clients. We need to consider the number of bit rates inside the mega manifest. In the evaluation setting, we consider different network traces and also different content types. And based on these bitrate ladders that actually exist in the industry, for example, TEO, MUX, Bitmoving, Pensive, and Twitch, we compare the performance ARTEMIS with 29 bit rates inside the mega manifest with the different size of the ladder you can see here. In the first scenario, I'm going to show that the performance of ARTEMIS regarding changing of the clients, changing the requests of the clients. You can see here that the origin server encodes the all content according to the different bit rates based on the OTL. We consider 50 players here based on the LOL plus ABR with different network with the specific network trace, 10 and then 6.5. In the first scenario, we are going to show that to apply the Twitch ladder on the encoder side, and the next one we are going to use ARTEMIS. Here, the available bandwidth showing here that we have a step here, and then there are many requests by the clients. Here, you can see that based on this throughput that we set. And then Twitch ladder is showing here by these horizontal lines. And you can see here that all requests by the players should be served by 3.75. But in ARTEMIS, we can adaptively change the OTL and then change the ladder and cover those requests at that area. You can see that, for example, here, the all requests by the clients, served by the exact bitrate that is provided in the OTL. In terms of the different parameters, for example, quality improvement, we have a good improvement here, and about, for example, here, as you can see, about 11% of the improvement on average, different with compared with different ladders, TEO, Bitmoving, MUX, and Pensive and Twitch. And also here we show that the improvement by the ARTEMIS over different network traces and ladders on the end-to-end latency, we have improvement about 18%. And also we consider the stall that we improve with 36%. So ARTEMIS is the adaptive bitrate ladder optimization for live video streaming, and is end-to-end and is based on the context and content. And in the ARTEMIS, we propose mega manifest and also OTL, how to select the OTL, and is the multi-objective performance improvement and reduce end-to-end latency, stall, and improve the quality of experience. Thank you so much for your attention. I'm glad to answer your questions here.